All right, I'm throwing some extra information out for you guys about our next topic. That way, if you're absent or you need extra help, you can refer to this video. Our next topic is about magnets. Hey, magnets are fun. Some of my first physics lessons involve magnets. If you think about your toy trains that you play with, Thomas the Tank Engine, they connect with magnets, and we know that magnets can attract or repel, and we can use this for fun or in many other purposes. We can use this for communication, for healthcare, in chemistry. It goes on and on and on forever. Magnetic fields are everywhere. The Earth is a huge magnet, and we're going to talk more about that in this chapter. There are various materials that are magnetic. The most common material that we deal with that can be magnetized is iron. Whoa, let's undo that. We got a little bit crazy on that one. So iron is something that can become magnetized, and because of its electron configuration or its atomic structure, it can take on what's called a magnetic moment. So it can be easily magnetized or not magnetized. Another one that I'm interested in myself is gadolinium. Gadolinium is a metal, it's pretty rare, and GAD, as we call it, is used in magnetic resonance imaging. So when you place gadolinium in a magnetic field, it will become magnetized, and we can use this as a contrast agent to look at various structures on MRIs. When we come back together, I'll demonstrate and talk to you about how this works. But let's move forward. So, hey, some materials can be magnetized, and they're said to be ferromagnetic. There are also two other types of magnetism that you'll talk about eventually when you study more physics, paramagnetism and diamagnetism, but for now we'll stick with ferromagnetic materials. Some things that you already know about magnetic fields is that is that they have two poles, a north and a south pole. So we're looking at two different magnets here. And we know that when you put a south pole near a south pole, they will repel. So these are forces of repulsion. When you put a north near a north, they'll repel, and a north near a south, they attract. So opposites attract. So right here, we have opposites. And these two are like poles. So if we circle our poles that are interacting, south and south, they're like, they repel. North and north are like, they repel. South and north are opposite, and they attract. So these are examples of bar magnets. And bar magnets, just like all magnets, have two poles, a north and a south. A magnetic pole, again, north and south. Since all magnets have north and south poles, they're said to be dipoles. The prefix di meaning two, and it's interesting, there is no, magnets are always dipoles. There is no such thing as a magnetic monopole. They don't exist. So here's a little thought experiment. If we take a magnet, which is one big bar magnet, and break it in half, you can't isolate the south pole or isolate the north pole from each other. You can't create an isolated south pole without creating a north pole. So again, when you break this magnet in half, you'll create a north and a south. If you break that half into a quarter, again, you'll create more norths and souths, and so on and so on and so on. So if you break these things all the way down, let's say even to matter, let's just say the size of an electron, it will have a magnetic property with a north and south pole. Now from chemistry, we know that there, and this is extra, we know that there are four quantum numbers, N, L, M, and S. N is which energy level it lives in. That's 1, 2, 3, or 4, and so on. Whole numbers. L is which sublevel. S, P, D, or F. M is which orbital within the sublevel they live in. And then S is a property called spin. All electrons have this property called spin, and spin can be up. Actually, I drew that wrong. So let's just undo it. They could be up spin or down spin. So if we looked at an orbital, the electrons could be either up or down spin, and that spin could be positive 1/2 or -1/2. So if I drew an electron that has, I don't know, a positive spin, so we'll put an E there, and then one that has negative spin, put an E there. This spin will be in this direction, and this spin will be in the opposite direction. So this and when charges move, we'll talk more about this now, and they could translate, move in straight lines, or rotate like we're seeing here about an axis like the Earth spins. They create a magnetic property, and let's just say that, I don't know, that this could be the North Pole, and that's the South Pole, and this is the South Pole, and that's the North Pole. So the orientation of the magnetic field is determined by the direction in which the charge rotates in space or spins. So physics and chemistry are deeply connected. Here's a little secret. Physics is the mother of chemistry. So it's interesting. So physics leads to chemistry, chemistry leads to biology. So really the physics is the parent of all sciences. Such a beautiful thing. Too bad we study it last in many instances. Now, magnetic field lines, because of the fact, just look at this magnet. The magnetic field lines are lines of, we'll call them, I don't know, force that that are associated with all north poles and south poles. So again, we have a dipole, a north and a south pole, and I want you to realize one thing by looking at this illustration, that the magnetic field lines come out of the North Pole and they go in to the South Pole. So this is a lot like a dipole with charges. So we have positive and negative. So the field lines will come out of one and go into the other. But one thing about these magnetic field lines, if you look closely within the magnet itself, the magnetic field lines are circles. So all magnetic field lines form closed loops. Always. So, because it's impossible to have a North Pole and a South Pole isolated from each other, there are no such things as magnetic monopoles. So now I'm going to make a window with one of our other tools, and I'm going to create a window that we can use to determine the field intensity. Now I always use my hand. I'll say the number of field lines per unit hand. You can't see my hand in this presentation. So if we take this window, see if I can grab that one, and we'll grab and dupe it. If we look at this window, we have 3 field lines per unit hand. I'm going to dupe it. Whoops. Let's try that again. Control D. There we go. If I come out here, the field, I have 1 field line per unit hand or per unit area. One more time. If I come out over to this location, I have 3 field lines per unit hand. So if we look at these regions, and let's just make one more so we can put one up on top. And I'll draw, and I'll use symbols. S is strong and W is weak. Since we have a lot of field lines per unit area, here the field is strong. Here, again, the field is strong. Out here, the field is relatively weak. And if we went way out in space, like out here, we know the field would be weak because the number of field lines per unit area is going to be small. The closer you are to the magnetic poles, the stronger the field. So the field is really strong near the South Pole. The field is really strong near the North Pole. And this can have some interesting effects. From an astronomy standpoint, we'll just say that. We'll talk about how the Earth's magnetic field does some interesting things and puts on some awesome shows. So there's a lot of exciting things to talk about within this chapter. Like I said before, the Earth is a magnet, and this is interesting. We have a geographic North Pole and a geographic South Pole, but there are also magnetic North and South Poles. And most people are under the impression that the North Pole is the North Pole of a magnet, and the South Pole is the South Pole of a magnet. but actually the geographic South Pole, which is not the same location as the magnetic pole, uh, is actually a North Pole. So if we look at this picture, this geographic South is a magnetic North Pole. The geographic North is near a magnetic South Pole, and the Earth's magnetic field is similar to that of a bar magnet. And I just want you to pay close attention. Now, do this in red. The magnetic field lines come out of the North Pole and go in to the South Pole. Now, there's a couple errors on this slide, so I'll just bring these to your attention and ablate them. This is actually a field line that's coming out of the South Pole. We'll just ablate that. This is a field line that's going out of the South Pole. Really, these vectors should go in, but it's not a big deal. The difference in the angle that's formed between the geographic North Pole and the magnetic pole is called declination. That's important for Boy Scouts because they use their compasses to navigate. In this day and age, we use GPS to navigate. It tells us where to go. I actually use the stars to navigate. I use Polaris, the North Star, to determine which way north is. Or I use the sun in the daytime because the sun is usually in the southern portion of the sky at midday. So let's read this slide together. The Earth is a magnet, acts like a bar magnet. The Earth's North Pole is actually a South Pole. South Pole is a North Pole, magnetically speaking. And the Earth's poles are not located along the rotational axis. So the Earth will rotate around this dashed line, and the magnetic poles do not line up. Now we recently, unfortunately we were unsuccessful. We tried to observe the aurora borealis because there was a blast of energy that traveled from the sun. And unfortunately, we were not able to observe that at this latitude, at this location on the planet Earth. But the Earth's magnetic field, I want to say this before we go forward, is relatively strong nearest to the poles. And these charges that will travel from the sun, which are being spit out of the sun, charged particles will interact with the Earth's magnetosphere, which is what we're seeing. And they consolidate at these locations, and when those charges interact with other atoms within the atmosphere, they'll give off light. That's on my bucket list. That's one of the things I'd like to see, is either the aurora borealis or the aurora australis, which is in the southern hemisphere. I've never been south of the equator in the southern hemisphere. It's one of my goals in my work, in my life. And another thing I'd like to see is the constellation, the Southern Cross. Someday. Now, if we look at a bar magnet, actually two separate bar magnets, and let's just add one thing to this picture. This North Pole would also have a South Pole, and this South Pole would actually have a North Pole because they're dipoles. Just for a complete picture, these magnets will interact with each other in lines of force because magnetic field lines will come out of the North Pole of the top magnet, originate here, and terminate in the South Pole. And one thing that is useful in using big bar magnets, let's just call these big fat bar magnets, is that the field that's contained in between, in this location within that region, is going to be uniform or constant in strength. So it's the same value everywhere. So it's almost uniform. But if we come out here and look at the edges of the magnet there and there, these are called the fringes. And the fringe fields are not uniform. So there are many instances when we want to create a strong, constant magnetic field. When we're steering charges. More on that soon. There's some applications of that in physics, or let's say if we wanted to perform MRI, we want to create a constant magnetic field. That magnetic field would look like this. So the line spacing is the same everywhere. And we can do that with a bar magnet, or you can do it with a big coil of wires like you would see in a speaker, and that's called a solenoid. We'll make some solenoids together and play. Magnetic fields are represented with the letter B. So let's have a little discussion. F, the letter F stands for force. The letter A stands for acceleration. The letter M stands for mass. B in physics is just a letter we chose, is the magnetic field. So the magnetic field is often expressed with the letter B. It is a vector because it has a strength and a direction. So if we go back, we represented the magnetic field with vectors. So these are magnetic field vectors, and their orientation is down in this picture, so that's the direction, and the strength again is the number of lines per unit area. So if we added magnetic field lines, can you predict what's going to happen to the strength of the magnetic field? Think about that. What happened? We went from 2 lines per unit area. When I drew this line through, we went to 3. The strength goes up. So the line density is related to the strength. So again, we refer to this as the B field. I just call it the magnetic field. And the units for the magnetic field are Teslas, named after Nikola Tesla, who did work with electricity and magnetism. A fantastic and mysterious man. And the Tesla has very unusual units. It's newtons per amp meters. Another unit for the magnetic field are Gausses, named after Carl Friedrich Gauss. We used Gauss's law recently to come up with the strength of the electric field for charges, but we very rarely use Gauss's, and 1 Gauss is 10 to the negative 4 Tesla. And the Earth does have a magnetic field, which is about 0.5 times 10 to the 4 Tesla, or 5 times 10 to the negative 5 Tesla. That's 0.1, 2, 3, 4 Teslas. So the Earth's magnetic field is really weak. That's about a half a Gauss. Now, MRI machines commonly will have magnetic fields which are much stronger than the Earth's magnetic field. They'll come in at about usually between 1 to 2 Teslas. So this is, let's just put this in perspective in terms of order of magnitude. 1 to 10 is about 10 to the 0 Tesla. That's not saying it's 0, it's saying in the ones. Remember, 10 to the 0 are the ones, 10 to the 1 are the tens, 10 to the 2 are the 100s, 10 to the 3s are the thousands, and so on. Now this one is of order of magnitude we stated before of 10 to the negative 5 Tesla. So this is weak, and the MRI is relatively strong. It's 5 decimal places stronger, which is, let's do the math here. You're talking about 100,000 times stronger. So the Earth's magnetic field is about 100,000 times weaker than an MRI machine. MRI machines are really cool to operate. I shouldn't say play with. We operate them, and you can demonstrate some funky physics in fields that are that strong. So the MRI machine was developed as a result of fantastic work of physicists. And if I'm not mistaken, the gentleman who, let's say, invented the technology of MRI is a Nobel Prize winner. I think his name is Ray Damadian. More on that later. Now, a long time ago, about 3 or 4 slides ago, we said that moving charges, remember those electrons that were spinning up and down, set up magnetic fields and so on, something like that. Rotating charges create magnetic fields. I'm just going to erase that for now because it's not critical. Rotating charges have magnetic fields, but also moving charges, current carrying conductors. So this black line is a wire that carries electricity upward, will set up a magnetic field, and those magnetic fields are described using what's called the right-hand rule. And that right-hand rule or better yet, let's back up a second. This black line is representative of current. So current carrying conductors will set up, look at this picture, and I'll do this in blue, magnetic field lines. So in saying this, electricity, current, gives rise to magnetism. So electric currents will cause magnetic fields. I'll demonstrate this for you. And this is a famous experiment which was performed by a Danish physicist, not the Danish pastry. He's a Dane, that's where he's from. But anyhow, current causes magnetism. By the way, that guy was named Ørsted, and he did a famous experiment to try and disprove, if my memory serves me, that he said that electricity did not cause magnetism. When he performed the experiment, he found the opposite. So we'll play with this together. The way we determine the orientation of the magnetic field, if you look, these magnetic field lines are circles, they're always circles, is the right hand rule. So we take our thumb and point our thumb in the direction of the current, and then always use our right hand to do this. The way our fingers curl, so if you look at your fingers are curling in this direction, the magnetic field is in that direction. So this upward current will cause a magnetic field in this orientation, as we can see in the picture. It's hard to say if I guess it's counterclockwise according to the way we see things. If we ran the current in the opposite direction, down, our fingers would curl in the opposite direction, and the magnetic field just changes its orientation in space. We'll look at many examples of this. Another thing, you can take a ring and run a current through this ring in this direction. So we'll say the current is going counterclockwise. So I'll draw that in black so we can stick with our convention. There, if we take our thumb at this location and point it up, my fingers will point out of the page. That's towards you. You're observing this video. If I take my thumb and grasp the wire at that location, the current is in this direction. Again, my fingers will point out of the page. If I point my thumb in this direction and curl my fingers inside the loop, they'll point out of the page. And down here, the current is in this direction. When I grasp it, my fingers will point out of the page. So inside of this ring, a magnetic field will come out of the page, and outside of this ring, everywhere on the outside, those magnetic field lines will point into the page. And we could represent vectors, magnetic field lines, with arrows that point in various directions. I'll just stick with blue. This is a magnetic field that points up. This is a magnetic field that points down. This is a magnetic field that points to the right. Whoops. This is a magnetic field that points to your left. So we're going to stick with these conventions. Now this is a magnetic field that points, so I'll put a dot there, that's out. Another way besides dots, sometimes they'll draw a circle and put a dot in, that also is out. The way we draw magnetic field lines into the page, so out here we'd have a magnetic field that points in, are X's. Or again, a circle with an X, that is also in. So magnetic fields can point in any direction, up, down, right, left, into the page or out of the page. We'll practice this right hand rule quite a bit. Up, down, left, right, third dimension is in, which will be X's, or circles with X's, or out, which are circles with dots, or dots themselves, whichever you prefer, and so on. So there we go. So we have a magnetic field that points in, and here we have a magnetic field that points out. So if I grasp this, and this is, you're going to see some wonderful art in this. If I grasp this with my right hand, oh, this is going to be tough to draw. If this is the direction of the current, we'll stick with black. If this arrow were a current carrying conductor, a wire, when I grasp it, my thumb will point in this direction. Oh, that's my thumb. And when I grasp this, if my fingers curl on top of the wire, my 4 remaining fingers will point out of the page. And then if I continue to rotate my fingers down and through, this is going to be pretty difficult, my fingers would point into the page. So again, those magnetic field lines that will exist around this current carrying wire will be loops, and they go in and then up and out. So I'll try and draw. This is going to be tough. Whoop, like that. Whoop. You got it. So we get these loops. Very hard to see in 2 dimensions. So we'll orient the wire a little bit differently and observe the magnetic field. Now, which of these are true? So we have a current carrying conductor pointing to the right. If we use the right hand rule and grasp this wire, that magnetic field will make complete loops. So one thing you need to know, on above and below will be different values for the field. If this is out, then this one has to be in. Or if this is in, this one has to be out. So these are impossible answers, because again, the magnetic field will have to make closed loops, so you'll have to have either X's or dots on one side or the other, the top or the bottom. If we grasp this wire and my thumb points in this direction, let's draw that in black, the magnetic field will come out of the page on top and go into the page on the bottom to make closed loops. That's D. I would go to YouTube and watch a video on how to find the magnetic field for a current carrying wire. There'll be plenty of options to see that. One that I totally recommend is AP Physics Lectures.com. This gentleman does a fantastic job at demonstrating this, but we'll be doing this together and it won't be an issue. Now let's take a look at these pictures. In which direction will the magnetic field exist for a current carrying wire that's below? So now that current carrying wire is into the board. In, because we have a wire with an X. Now, which way will my thumb point if we go back and use that right hand rule? My thumb always points in the direction of the current. So if my thumb points into the board, my fingers will curl clockwise. See? Which way will my thumb point in this case? The answer is down. So my thumb will always point in the direction of the current. Let's get rid of some impossible questions or responses. Why is this one impossible? Think about that. Letter A. Oh, it's because we have a magnetic field that's pointing out here and out. Remember, if one side is out, the other side would have to be in. And again, if one side is in, the other side has to be out. So it comes down to this. Now, if we point my thumb down on the left-hand side of the wire, my fingers will curl in, and on the right side that points out. Let's reveal the answer just to make sure we're on board. You got it. Nice job, Mr. Chestnut. You must have done this before. And this is and we'll end this video on this slide without performing it, because this is let's just say this is it's It's not a difficult problem, it's just an advanced example. So we'll come back together in a moment.